right, thanks everyone. The title of the talk is Commutative Algebraic Vision in the spirit of the workshop. And this will actually be two-part talk spread over 2 days. I wanted to say a little bit about this picture here. So this is a 3D reconstructed scene, particular landmark in Paris. And these red lines that you're seeing are indicating the locus where a certain type of camera is undefined. In fact, this is what's called a radial camera, which maybe I'll talk about at the very end of the talk tomorrow. But this is just to give you a sense that algebraic vision is a subject that involves some people working in mathematics and also people working on more applied topics, such as how do you actually make a 3D model like this one. Okay, so the goal of the talk is to explain what is algebraic vision. The title slide was to convince you that there is sort of an applied aspect to this whole subject. Here's my clicker, but there's also a pure side, and I'm very hopeful that if not today, then certainly tomorrow, we'll be able to state some problems which would really benefit from fresh eyes, particularly people with a commutative algebraic mindset. A lot of the questions I talk about today are motivated by applications, but they're very much in the realm of things mathematicians do. So there are two essential references. One is quite canonical from the computer vision point of view. This is a book, sometimes called the Blue Bible, by I don't think I want to connect to the archive. But there are actually links embedded in these slides. So if they get posted later, then you'll get to check out these references if you like. So this book by Hartley and Zisserman is considered a classic in the field. It explains a projective geometry approach to pinhole camera and reconstructing scenes and things like that, which we'll get into in great detail. Lots of projective geometry in Hartley and Zisserman, almost no algebraic geometry in Hartley and Zisserman. Fortunately, we live in a time after 2023, and there's a nice survey written by Joe Khalil and Kathleen Cohn, which is available on the archive, entitled Snapshot of Algebraic Vision. So please do check out this survey if you get the chance. The tentative plan is I'll talk a little bit about the basic concepts in algebraic vision. We'll have a running example, which is the perspective endpoint problem, also known as camera resectioning. And maybe today, but certainly tomorrow, we'll talk about some other problems, namely triangulation and reconstruction, and what sort of interesting things could be on the horizon with those problems. Okay, but first of all, you have to start. Okay, vision is about how we perceive things, and in particular, cameras are a very kind of classical way of producing images, and nothing's more classical than the pinhole camera. So let's review how this works. So pinhole camera has a center, or which physically could be a small aperture that focuses a narrow beam of light, and mathematically this is modeled as projection through a point onto a plane. So you have a point in R3, X, Y, Z, and if you choose the coordinates very smartly, then in particular, you would want to choose this plane to be Z equals 1 and the origin to be the center of projection. Then you get this nice rational expression for what the projection of X, Y, Z should be. So it's X over Z, Y over Z. Very simple. Okay, and this is not linear. Okay, so we're in nonlinear territory, but it's almost as good because it's projective linear. So if I write this point, the projected point, that's this green point here, in homogeneous coordinates, then I should probably stop. Okay, so I can write this point in homogeneous coordinates. I think most people in the audience know how to do this. Then that's equal up to scale to just the original point that you started with in X, Y, Z, but now you're thinking of it as a point in P2. So I'll be using this predicate sim to denote when two vectors represent the same point in projective space. It's actually really important to mind the fact that this is an equality up to scale. And the advantage of working with x, y, z is that you can see that this is actually just a matrix times the 3D point in homogeneous coordinates. Okay, and so this is what we call the camera matrix in this very particular coordinatization of the pinhole camera. Okay, any questions about this slide? Okay. Now, we chose the coordinates really smartly on that last slide. So what happens in general? Well, in general, there's 3 coordinate systems one would care about. There's a coordinate system in the world, maybe, like if you're making a map of Toronto or something like that, you have a coordinate system there. And then there's a coordinate system for the camera as well as the image points. And let's think about what a general linear projection would look like. So general linear projection from P3 to P2, that can be represented by a 3x4 matrix. And when you start counting degrees of freedom, which as we all know are really just dimensions of algebraic varieties, we see it has 12 minus 1 degrees of freedom. We consider this up to scale. And if you want to know what those, is there some physical meaning to those degrees of freedom? One thing you can do is take the RQ decomposition of a matrix representing your linear map. RQ decomposition is QR decomposition, except you reverse sort the rows of your matrix and transpose. Right, so if you have an RQ decomposition, it's going to have some factor on the right. Confusingly, this is the Q factor, which is written in block form as R and T, where R is an element of the special orthogonal group. So this is a 3x3 rotation matrix with determinant 1. And then T is sort of what we call the translation vector. And R and T in total have 6 degrees of freedom. And they tell you the location and orientation of your camera in space. And so for this reason, these are called extrinsic parameters. And notice that RT itself is a 3x4 matrix. So it's a camera. And we call any camera that can be written as in this form, at least up to scale, a calibrated camera. So then the question is, what does this other bit, the left bit of the RQ decomposition mean? Well, in computer vision, this is usually denoted as K. This is called the calibration matrix. So it's got these entries alpha x and alpha y, s, x naught, and y naught. So x naught and y naught basically tell you something about the center of the image. S is a skew parameter, which in many cases is 0, though not always. Alpha x and alpha y are telling you something about the focal length and the width of the pixels in the image. So really, you can think of this as an affine transformation in P2 that sort of turns the camera coordinates into the image coordinates. All right, so altogether, we have 6 extrinsic parameters comprising the calibrated matrix and 5 intrinsic parameters. 6 intrinsic parameters describing the calibrated camera matrix and 5 intrinsic parameters describing the calibration matrix. And oftentimes these intrinsic parameters are things that you know, or they can be estimated, but not always. So it's interesting in these problems to consider both calibrated and uncalibrated settings. Okay, so far so good. Please do feel free to slow me down with questions as well. Okay, so it's kind of fun to look at the history of this subject. So back in 1773, there was not anything called algebraic vision, but there was this guy, Joseph Louis Lagrange, who wrote a paper about how to solve a particular problem called, which nowadays we call the perspective 3-point problem. So he was certainly a pretty notable person who may have the claim for the first paper in algebraic vision. Maybe you could go back further, I don't know. Some other notable folks like Hesse, who worked on what we now call the 7-point method for reconstruction from two views. That was in 1863, Krell's journal, I believe. We also have some lesser known names here on the right. So another guy who worked on P3P was this guy Grunert. And you can see on the first page of his paper, he's got a system of 3 polynomials and 3 unknowns. So very topical. I'll explain where those come from. And then there's this guy, Krupa, who explained how you could do 2-view reconstruction with just 5 points if you know the calibration matrix, although not quite in that terminology. Okay, so first up is perspective 3-point. So how does this work? So you're given the input data of 3 points, Q1, Q2, Q3, and P3, and you have matching points, P1, P2, P3, and P2. And your goal is to produce a calibrated camera, RT, that projects each QI onto the corresponding PI. Okay, now if you're wondering, like, how do I think about this problem? Well, we're in a city with nice landmarks like the CN Tower, for instance. And one of the problems that people really care about is sort of visual localization, where if you take a picture of wherever you are, basically, can you somehow retrieve the location of where the person who took the picture is? And well, if you have some sort of black box that can start matching points in your query image, these are these PIs, to points in known landmarks, such as the CN Tower, with a known location, then you can start to play this game of how do I estimate the location of the parameters. And so if you have exactly 3 such matches, that's where this P3P problem arises. Okay, so here's a picture of P3P. So basically, what I'm looking at here is, originally I had a camera with the origin as the center of projection. And now I'm going to look at what happens when I apply rotation and translation to 3 world points that are often some other coordinate system, CN Tower coordinate system. And then I say that I want these to be equal to the 2D projections up to scale. So in fact, not only are the rotation and translation unknown, but also these scalars are unknown. So how far along the ray from this origin do I have to go to scale each point in P2, or each representative of a point in P2, up to meet the projection using this calibrated camera matrix? So everything blue in this picture is unknown, green and magenta are given. And so what were the equations that Grunert wrote down? Well, he said, look, I don't think he even really mentions the rotation and translation. He's just looking at this as a purely geometric problem. He's only interested in the depths. And but if you want to get the equations that he wrote down, what you can do is you can essentially pick any 2 pairs of rays. So like, let's say Q1 and Q2 both give me a ray from the camera center, and apply the law of cosines. So let's say I did Q1, Q2. Well, then if I choose appropriate representatives of my Qs and Ps, then I could compute the length of this side. So that's just the distance between Qi and Qj. And then the lengths of these dashed lines, of course, are just the lambdas if you normalize the P's appropriately, which I think I said here. Pi should be unit length. And then, so you have a triangle with 2 unknown side lengths. One side length you know, but you also know something about the opposite angle. That's coming from these P's. So in other words, this system of equations that Grunier wrote down is just the law of cosines applied to every pair of triangles you have in this picture. And that would allow you to solve for these three unknown depths. And so it's three quadratic equations and three unknowns. You expect that for generic data, there should be 8 solutions, and indeed that's the case. Okay. Questions? Oh yeah, we'll get there. That's right. So I'll explain how to get R and T maybe 2 slides from now. Okay, so here's maybe like a bit of a cheeky take on algebraic vision. So I claim that all the interesting problems that, at least in the scope of this talk, are going to be formulated as follows. So I have a map from an algebraic variety X, which represents the space of unknown states. That map is called pi, could be a rational map. And let's say it's onto a space of parameters, like in Paul's talk earlier. And what we're given is a measurement of some true data, which is actually the image of this map. But of course, the measurements are noisy, and they might not lie in the image, or even up to closure, they might not lie. They might not lie in the closure of the image. And so almost every problem in algebraic vision is either directly solving or motivated by a version of this problem where your goal is to recover some approximation of the input signal. Maybe this is even like a general way of looking at applied algebraic geometry. But at least for the purposes of this talk, I'll try to tell you that it's useful to think about all the various problems in this framework. So let's do it for P3P. Well, actually, what's so special about 3 points anyway? Well, if we had n points, the natural map for us to look at would be sending an element of the special Euclidean group to n projections of the n projections of the given 3D points, right? So here I've just written out the standard pinhole projection in local coordinates so that I'm mapping into a Euclidean space. Okay, and if you adopt this point of view, then there are basically going to be 3 regimes that are interesting to study. One is the minimal case. So the minimal case, so all of these regimes are just determined by counting dimensions, right? So you have a space of unknowns, you have a space of measurements. If one's bigger, if the space of unknowns has bigger dimension, this is probably an under-constrained problem. So P1P, P2P. What is the case where we have a sort of a minimal, well-constrained problem? That's when the dimensions of these 2 spaces agree. So that would be exactly when there are 3 points. And of course, in applications, you will have an over-constrained problem. So most likely, if you're taking pictures of the CN tower and running a black box matcher from points to landmarks, then you're going to get many more than 3 matches. And so the over-constrained setting is also something that people are interested in, maybe the most interesting from an applied point of view. Okay, so now to answer Paul's question, what do we do with P3P here once we've solved for the depths? So we plug it into Grobner-Basie's homotopic continuation. We get out 8 solutions for these depths, and we can recover the rotation using the following formula. Well, it's expressed in terms of the unknown depths and the 2D points and the 3D points, Q1 through Q3. I'm making a slight change to the problem here where I'm actually just saying each Qi is a 3×1 vector. That's because there's a cross product involved. So somehow working in 3 dimensions is nice because there are lots of formulas involving this cross product. Anyway, this is a formula that allows you to retrieve the rotation given the depths. And once you've got the rotation, getting the translation is a cinch. So this is, in a nutshell, one of the ways that you could solve P3P. You have a black box that solves some polynomial system, and then you recover these quantities of interest before you eliminated everything but the depths. And yeah, it's a long time now since the 1700s, but people are still writing papers about P3P and publishing them in decent venues. So there's a paper in CVPR 2 years ago, Yachik Ding and collaborators, where they make some slight improvements to the state of the art in solving P3P. And this is like, I don't know, less than a microsecond, certainly per run. And they actually don't use this exact setup. They do something a little bit more sophisticated involving singular pencils of conics, which if you think about it, this is a system with 8 solutions, but there's an obvious sign symmetry here. If I sort of reflect the picture through the origin or change the sign on each depth individually. So that reduces to a quartic. And then quartics, as we know, can be solved using resolvent cubics and auxiliary square roots. So actually, somehow P3P is really something that you can solve with univariate cubic. But this is just meant to give you an example of what people are calling minimal problems in computer vision. Okay, but so what does this have to do with the over-constrained regime? Well, okay, so if you have more measurements than unknowns, recovering an exact solution with noisy data is impossible. So what can you do? Well, in practice, and people like Tomasz Pydla in the audience can tell you, you have to do some sort of optimization. And so a common cost function that people try to minimize is what's called the reprojection error. And all the reprojection error does is it says, okay, for each putative match between a 3D point and a 2D point, what's the closest I can get in the 2D Euclidean metric on R2 from the projection under A of Q to P. So this is one choice of cost function. It's a nice rational function. And where minimal solvers are actually used is they're used to initialize standard nonlinear least squares methods for solving these problems. So in fact, a lot of the reason why people still care about developing minimal solvers is so that they can get a warm start to this optimization involving many more measurements than unknowns. There's actually even more to it. So oftentimes, many of these matches are erroneous, which means you want to throw them out of the cost function entirely. And so there's a bit of a dirty game people play called RANSAC. It's an acronym that stands for Random Sampling and Consensus. And it tries to basically fit 3 points at a time, see how many other points agree with the estimate, and then go on until some budget is exceeded and take the best estimate arising from that. So it's completely heuristic, but it's got some nice math going on underneath it. Question?
Yeah, so the distribution of the noise doesn't involve
how do you mean?
I think the cost function because like if you have the that it doesn't show up.
Well, I guess, yeah. So, I mean, you could, I suppose, assume that your 2D coordinates are corrupted with Gaussian noise or something like that and try to model it based on that assumption. Yeah, but in practice, you don't know the noise. So there's not too much to say, I think. Yeah.
What I know is that most of the vision is on AI these days.
Uh-huh.
So this also, I mean, the solvers also this in this direction.
Well, there's a little bit of work combining minimal solvers and AI. But yeah. I would say it's a frontier. People are working on this for sure, but there are not too many papers. Well, I mean, in the practical scenario, you'll probably get more than 3 points.
Sometimes people comment on the question of noise. You don't know the noise, but the noise is captured by the data. So that's where AI comes.
Yeah, I mean, I would say that optimizing this cost function in some sense is a solved problem, but you still need to initialize it and properly model the problem. And so this is where I think algebra people can contribute the most. Okay, right. So, and maybe you would want to know, like, okay, so in practice, people are using something like nonlinear least square, Levenberg-Marquardt to minimize this cost function, but it is rational function, so maybe you can count critical points. And we do actually have a conjecture for this particular version of the problem where you have an uncalibrated camera matrix that's unknown and you're trying to fit it to n 3D, 2D matches, how many complex critical points there are. And we really have no idea how to prove it. So you can check out my paper. This is joint with Aaron Connolly and Jesse Laux-Tavitas to learn more. Okay, now, so that was the over-constrained regime. What about the under-constrained regime? Well, that seems like it's also hopeless, right? Because you don't have enough measurements to recover even up to finitely many possibilities, like 8 in the example of P3P, what the true solution is. But I think from our perspective, this is already an interesting thing to study. So here's an exercise that you can do maybe during the coffee break or something like that. Let's say you have two 3D, 2D point correspondences, so Q1, P1, Q2, P2, and they're viewed by some calibrated camera, A. Now, so the camera center, by the way, this is the point where this linear projection is undefined. And if your camera is calibrated, there's a nice formula for what that camera center should be, negative R transpose times T. And if these point correspondences are suitably generic, then there's a quartic constraint which this camera center must satisfy, which it turns out is independent of the camera orientation. And actually, I drew a picture with the help of Tixie of what this quartic constraint looks like. It's actually pretty simple. It's a surface of revolution obtained from a circle. But unlike a normal torus where you are rotating around a line that doesn't intersect the circle, you're actually rotating around a line that does intersect the circle. And as a result, you get these two sort of singular points, which are like, maybe where the stem of an apple and the core are or something. And those are exactly the two 3D points that you start with. So here's a question I don't know the answer to. If you have two generic correspondences like this as before, could you find a constraint on the camera orientation that's independent of the location? The answer is surely yes, but I don't really know how to do it. So maybe this is something we can warm up with on Wednesday. So do I have 15 minutes? Or
Started 4 minutes late.
oh, okay. So maybe I'll say some things about triangulation and early. Okay, so that was resectioning, which basically says we're given 3D structure, 2D projections, figure out where the camera is. Triangulation is a little bit different. So here we're given the cameras. So let's say I have, now I need more than 2 cameras to make this an interesting problem. So I'm given an arrangement of cameras, A1 through AM. And what I can do is try to put this in the framework of that we had proposed earlier, which is triangulation tries to recover the 3D position of a point from all of its 2D projections. And so what that means is essentially you have this rational map from P3 into M copies of P2, and you would like to invert that rational map to recover the 3D coordinates. Okay, and so the Zariski closure of the image of this map is something that people have studied a lot in algebraic vision. It's called the multi-view variety associated to this camera arrangement A bullet. And well, I said there's a lot that's known, so here's kind of a big summary of some work by Aholt, Sturmfels, and Thomas. So one can look at Zariski open subset of the camera space. So certainly within this Zariski open subset, I'm only going to look at 3x4 matrices of rank 3, but there will be some other genericity conditions as well, so that the following 3 conditions hold for any camera arrangement in that open set. So first of all, the vanishing for any A bullet in this Zariski open subset of M tuple camera space, the vanishing ideal of the multi-view variety has an explicit multilinear or universal Grubner basis. So it's this means a Grubner basis for any possible term order on the polynomial ring proj of that gives you proj of whose proj is P2 to the M. So that's the first of these 3 results. The second of these 3 results is that these ideals are nice in other ways. So if you look at the multigraded generic initial ideal, so you change coordinates in each P2 factor independently, you will get and take the initial ideal, you will get a square-free initial ideal. And these are called Cartwright-Sturmfels ideals. Elisa Gorla is an expert on these things. So that's another nice aspect of the structure of multi-view ideals. And thirdly, if you have at least 3 cameras in your arrangement, then I can look at a mapping that associates each camera tuple considered up to the action of PGL4. So I didn't actually say what that action is, but it's by right multiplication on each of the cameras simultaneously. So I can associate an equivalence class of camera arrangements with the ideal of the multi-view variety, which doesn't change if I multiply A by H inverse. I just multiply Q by H, something like that. What this gives you is actually, it realizes the quotient of this open set as a dense open subset of some multigraded Hilbert scheme. So sorry, it's dense and an irreducible component of that Hilbert scheme. Okay, so lots is known about multi-view varieties, particularly when you have a generic camera arrangement. It would be nice, I think, actually to extend some of this to the setting of resectioning. Notice that here, in the setting of triangulation, you are given the cameras, but in the setting of resectioning, you're not. So you actually have 2 distinct questions. One is the calibrated case, one is the uncalibrated case. Okay. So that's that. I guess I'll do a quick example of what these multilinear constraints vanishing on multi-view varieties look like. So here I've got 2 camera matrices. So this is the camera matrix we had from the first slide. And then here I've got a kind of reverse situation where I've got an identity block on the right and then a column of zeros on the left. And so if I project the same world point into 2 copies of P2, then I've got Q1, Q2, Q3, Q2, Q3, Q4. And I want to know, okay, what constraints do I get on these 2 projections up to scale? Well, the natural thing to look at is, here I've got a Q2 and a Q3 in this first projection, and Q2 and Q3 in the second projection. So how about let's look at the ratio of Q2 and Q3, since that will be independent of the scale. And that can be expressed using the first point and the second point as a ratio of the coordinates. You clear denominators, you get a nice bilinear binomial equation. Now, these were 2 special camera matrices, so it's not going to be binomial if you replace these with 2 general cameras, but it will still be bilinear. And in this case, we can actually extract the 3x3 matrix that represents this bilinear form. It's not too hard, so you can see that it's this blue matrix I have here. And this is an example of what's called the fundamental matrix of the camera pair. So all of these multilinear constraints associated to multi-view varieties and various generalizations thereof are coming from what are called Grassmann tensors. And I have a little bit of time, but I think I might save that for tomorrow.